Welcome to the deep dive. You know those amazing large AI models like ChatGPT or Llama, the ones doing incredible things,
Oh yeah, writing stories, code, you name it. Really impressive stuff.
totally redefine things. But well, what if there's a hidden danger? Something lurking in how they're trained that could actually make them
Yeah,
worse.
something called model collapse. It's a real risk, a critical performance drop.
And that's what we're diving into today, right,
Exactly.
Michael?
We're looking at some really cutting-edge research here. There's a paper, Strong Model Collapse, from researchers at places like FAIR, Meta, NYU, UCLA, top folks, Elvis Domatov, Yunzhen Feng, Arjun Subramanian, Julia Kempe.
Okay, so our mission for you today is pretty clear. We're going to unpack what model collapse actually is, why it's frankly a bit concerning for where AI is heading,
Uh-huh. And how it affects even the biggest systems we use.
and the big question, can we actually avoid it? We've pulled out the key stuff from this research just for you. So let's get into it.
Right. So at its heart, model collapse happens when AI models, especially these big neural networks, get trained on a lot of synthetic data.
Synthetic data, meaning data made by other AIs, not real-world stuff.
Exactly. Not photos people took or text people wrote, but stuff generated by a previous AI model.
Uh, okay. And that creates this feedback loop, doesn't it? Like AI learning from slightly distorted copies of itself.
Precisely. It's a dangerous cycle. The models start overfitting. They learn the patterns, quirks, maybe even the errors or biases in the synthetic data, not just the real world.
And that reinforces those errors generation after generation.
Yes. It skews things. It distorts the underlying pattern of real data the model is supposed to be learning. And crucially, it hurts the model's ability to generalize, to handle new things it hasn't seen before.
So what does that look like in practice? What happens when a model collapses?
Well, the outputs can get confused.
Weird.
You might see just plain gibberish, nonsensical answers.
Stuff that just doesn't make sense.
Right. Or it could amplify misinformation or stereotypes that were subtly present in the AI-generated data it learned from.
So when you interact with an AI and it says something totally off the wall, that might actually be a symptom of this, not just a random glitch.
It could very well be. We often just dismiss it. But yeah, model collapse might be happening quietly behind the scenes.
Yeah.
That definitely makes you think.
Okay, so the researchers jumped right into the obvious question, didn't they? Is this collapse thing inevitable? Or, can't we just mix in real data with the synthetic stuff to kind of uh, balance it out?
That feels intuitive, right? Just
Yeah.
add some good stuff back in. But their first big finding was actually a pretty strong no.
Really? Mixing doesn't fix it.
Not completely.
Huh?
They found what they call strong model collapse. It still happens even when you mix real and synthetic data, unless the amount of synthetic data basically drops to zero.
So just sprinkling in real data isn't enough.
It's not the magic bullet.
Yeah.
Simply mixing isn't sufficient to prevent the collapse from setting in.
And then there's that finding about the percentage that really stood out to me.
Oh yeah, the 1% thing. That's kind of shocking.
Tell us about that.
Well, the paper points out, and they show this visually in Figure 3, that even as little as 1% synthetic data in the training mix can still lead to this collapse.
1% in potentially massive data sets.
Exactly. Performance just hits a wall, it plateaus. You add more data, but the model doesn't get better like you'd expect. They even said it was worse than anticipated.
Wow, that really highlights how sensitive these training processes are.
It does. You can see it in the graphs. The test error just stops improving. It deviates way off from that ideal diagonal line you hope for, where more data means better performance. Even tiny bits of bad synthetic data mess it up.
Okay, that leads to the next big question they looked at. Are the huge models we have now, these massive LLMs, are they more likely to collapse than smaller ones?
That's a great question, and the general answer is yes, sort of. Bigger models do tend to suffer more, especially if the synthetic data is quite different from the real data.
So bigger isn't always better in this context.
Not necessarily. But here's where it gets a bit more complicated. There's a twist.
Okay.
The theory suggests there's this critical point called the interpolation threshold. It's roughly when the model is big enough to perfectly memorize or interpolate all its training data.
Right, I've heard of that.
So the research predicts that once you get past that threshold, making the model even larger can actually start to help again. It can mitigate the collapse somewhat.
Mitigate, but not prevent it entirely.
Exactly. It doesn't make it go away, but large models past that point might handle the collapse slightly better than models that are just at the threshold.
So it sounds like that double descent idea we hear about sometimes. where performance gets worse, then better again as models scale up.
That's precisely what they predict here for model collapse.
Yeah.
A double descent curve based on model size. The test error changes in complex ways. You can see it in figures 1 and 2 in the paper.
So how big your model is, that choice really matters for how badly it might collapse.
Critically. And looking at figure 1, for instance, it shows that very small models, they're never the best option for dealing with collapse.
Interesting.
Yeah, the sweet spot, the optimal size might actually be somewhere in the middle, an intermediate size, depending on just how much synthetic data you have and how good or bad it is.
So it's definitely not a simple bigger is better or smaller is better rule.
Not at all when synthetic data is involved. It's much more nuanced.
And the really compelling part is that this isn't just theory, right? They actually tested this stuff.
Oh, yeah, absolutely. They ran experiments to confirm it,
Mm.
both on simpler setups and on, actual language models.
Okay, like what? What did they test?
Well, first, they used the classic MNSDA dataset. That's the handwritten digit recognition task. They trained 2-layer neural networks on it.
And what happened there?
They found exactly what the theory predicted. As they increased the amount of synthetic data mixed in, those nice scaling laws where models get better with more data or size, they just slowed down.
Performance gains started to flatten out.
Exactly. They plateaued. Clear sign of strong model collapse. And it only really went away when the synthetic data fraction got close to 0. That's in figure 7.
And figure 6, what did that show?
Figure 6 looked at training only on synthetic data. And there, they found larger models were actually more prone to collapse, even in that regime where larger models are usually considered more robust, the interpolation regime.
Okay, so it holds up in image tasks. What about language? That's where everyone's focus is now.
Right. So they tested it with language models, too. Specifically, GPT-2 models.
Okay.
They trained them on a dataset called Babas Stories. And here's the interesting bit. Babas Stories was itself generated by another, more powerful AI, Mixtral 8x7b. So perfect test case for synthetic data effects.
Right, using AI-generated stories to train another AI, what did they find?
Well, figure 8 shows it clearly. On the left side, even putting in moderate amounts of this, relatively high-quality synthetic data still delayed how quickly the models improved. The scaling loss slowed down, hit plateaus.
So even good synthetic data causes issues eventually.
It seems so. And the right side of figure 8 really drives home that double descent point in practice.
How so?
Larger GPT-2 models performed better lower test loss up to a point. That point was the interpolation threshold, which for this setup was around 30 billion tokens.
Okay.
But beyond that threshold, the smaller models actually started doing better again. They had lower loss.
Wow. So just like the theory predicted, bigger models helped up to the threshold, but amplified the collapse after the threshold.
Exactly. It aligns perfectly. Larger models can make it worse past that point, but potentially mitigate it below that point.
Okay, this is sobering stuff. Knowing how common synthetic data might become, or already is, are there actually any ways to stop this? Any mitigation strategies that work?
Well, they looked into that too. The paper explores a couple of potential strategies.
Like what?
One is something called weighted single-step data mixing. Basically, trying to be clever about how you mix the real and synthetic data during training.
Maybe giving more importance, more weight to the real data.
Kind of, yeah. You assign different weights. It's based on some prior work.
Okay, and does that work?
The short answer is no. Not really.
Oh, why not?
The research shows pretty clearly, especially in figure 9, that if your synthetic data is low quality, the best strategy, the one that gives the lowest error, is basically to just throw away the synthetic data.
Give it a weight of 0, essentially.
Pretty much. The graph is U-shaped. The minimum error happens when the mixing coefficient, alpha, is almost 0, meaning you use almost no synthetic data. Any fixed amount you do use still puts a floor on how good your model can get. It still collapses.
So simple weighting doesn't dodge the bullet. What else did they look at?
They explored a more complex idea, dynamic or multi-step data mixing.
Dynamic mixing. What's that involve?
It's more involved. Inspired by other recent research, the idea is to try and iteratively improve the synthetic data quality. You sort of bootstrap it over multiple training steps.
Okay, that sounds promising. Maybe refining the synthetic data helps.
It can help recover the scaling laws, potentially. But there's a huge catch-22.
There's always a catch. What is it?
It's just highly impractical. It needs a lot of these bootstrapping. It needs huge amounts of real data to work with. And you constantly have to track what's real and what's synthetic through all these steps.
So computationally, incredibly expensive.
Hugely expensive.
Right.
And even then, figure 10 shows that performance still doesn't get as good as if you just use the real data alone from the start.
So it's mostly just neutralizing the bad synthetic stuff, leaning heavily on the real data you have.
That seems to be the main effect. It relies heavily on the real data anchor.
And what if you don't have a lot of real data to start with?
Then it gets even worse. If you have limited real data, this iterative approach can actually backfire. The test error can increase over the iterations. You get catastrophic model collapse.
Wow. So even the fancy methods rely fundamentally on having enough good real data.
It really seems that way. It
Yeah.
keeps coming back to the source. AI needs that grounding in reality. You know, you can't just keep feeding it copies of copies indefinitely without problems, like trying to bake a cake with only artificial ingredients. Like you said, you hit a wall.
So let's try and wrap this up. What are the big takeaways for everyone listening?
I think the main thing is model collapse is real. It's serious. It's not some niche theoretical problem.
Right. It affects even the best models we have now, and it doesn't take much synthetic data to trigger it, even small amounts.
Exactly. Which underscores just how vital real high-quality, well-labeled data is. Avoiding accidentally slipping synthetic data into your training pipeline is absolutely critical.
Yeah, it's not just about having tons of data, but knowing where it came from and ensuring its quality. The source really matters.
Absolutely. And also, remember that complex relationship with model size. It's not straightforward. Bigger isn't always better. Smaller isn't always better. There are these thresholds and nuances.
Definitely more complicated than it might seem on the surface.
For sure.
So, thinking about all this, it leaves us with a pretty big thought, doesn't it? Considering how much AI-generated content is just flooding the internet now everywhere,
Yeah.
and knowing how crucial real data is to keep these models healthy to prevent this collapse, what responsibility do we have? You know, as people using AI, creating content online, maybe even training models ourselves, what's our role in making sure there's still a healthy, authentic data ecosystem for the future of AI?
That's a really important question to chew on.
Definitely something for you to ponder next time you're interacting with an LLM or scrolling through your feed.